Welcome all of you. So, previously we saw one case study on life cycle assessment of coal fired power plant. So, there we saw like the system boundary was extraction of coal from mines, transportation, bringing it to power plant site where it is combusted, and then disposal. Like coal gets consumed in the form of electricity, it generates electricity and it leads to emissions, particulates and fly ash. Right. So, today we will see one more case study in some different area again concerning the environment. So, this case study is on waste to energy plant. So, on this here you can see the pictures of like municipal solid waste lying down in a dump yard or a landfill, and it is highly unhygienic and it contains lot of like biodegradable organic matter also, which keeps on releasing methane and other greenhouse gases. So, it is not good for the environment, and on the other side you can see the typical like say incineration based waste to energy plant, where the degradable biodegradable portion of this waste or the combustible portion of this waste can be burnt to generate energy, heat or electricity, and then again it has some emissions going back into the atmosphere, but then at least we are generating electricity which can reduce some of the power generation which is otherwise coming from the fossil fuel. So, waste to energy plant, it converts municipal solid waste into electricity and heat through controlled incineration. This does not mean that all the waste to energy plant are based on incineration only. Like in India, you would have some plants based on gasification, pyrolysis or even anaerobic digestion. Like if it is just food waste or animal waste, anaerobic digestion is a very good process to generate methane, and it can also come under the category of waste to energy. So, while waste to energy reduces waste volume and recovers energy, these incineration based plants, they emit lot of pollutants also. So, this is a case study which is a typical urban waste to energy plant which handles around 1000 tons per day of MSW, and then we will compare this proposed waste to energy plant against the conventional method of landfilling, which is here you can see on the left hand side picture. So, waste to energy plant, a schematic figure, it looks like this, where you have waste collected from different wards or different parts of the town or city, and it collected in the waste storage pit, and then with the help of crane it is fed to the incinerator. Okay. So, in incinerator like where the waste is burnt, the heat is obtained, again it is the steam based power plant. So, in boiler you have water, and the heat in the furnace obtained by burning of waste heats the water, converts it into steam, and that steam generates, rotates the turbine. The generator connected to the turbine sends electricity to the grid, and the gases which come out of the incinerator, mainly the flue gases, they have got lot of impurities, lot of particulates. So, they need to be cleaned through scrubber or the filter bag house before sending it to the stack through the chimney, and it goes into the atmosphere. And if there are any like liquid or solid waste, like mainly ash which is coming out from the bottom of the incinerator, that gets collected and it goes along with wastewater and ash, they can be sent to the wastewater treatment plant or for disposal, depending on like if we have usage for ash or not. So, that is a typical waste to energy plant. So, the goal and scope definition. So, in this case the goal would be to evaluate the environmental impacts for generating 1 megawatt hour electricity from MSW incineration. So, the process is fixed, the final product is fixed, and our objective is to estimate the environmental impacts. The second objective is to compare waste to energy option with landfilling in terms of GHG emissions and resource use. GHG emissions is one important thing, because there are emissions both from landfill as well as from waste to energy plant. But then in terms of resource use in waste to energy, we may be on a positive side to gain something because we are putting waste to use as a resource to identify environmental hotspots and improve the options in waste to energy systems. So, those are the goals or objectives of our study. The function unit, since it is ultimately generating electricity, and that is the service which would be provided. So, 1 megawatt hour of net electricity delivered to the grid is a function unit. System boundary, we are considering cradle to grave. Method use is a recipe midpoint indicator method, which has 18 midpoint indicators, and there will be 3 endpoint damage indicators. So, before we go for like inventory, let us see what this life cycle inventory is going to include, or what this life cycle assessment is going to include and exclude. So, it will include waste collection, which is a fuel here, like how much fuel is going into collecting that waste and then transporting it to the waste to energy plant, how much emissions are there through those trucks and transportations or through the in the collection strategies. Incineration and energy recovery, flue gas cleaning system, bottom ash, fly ash handling, residue disposal in landfill, or avoided electricity from grid. That would be on the credit side, because we make an assumption that since some electricity obtained from waste is sent to the grid, so it will reduce the fossil fuel load from the grid for that much equivalent amount of electricity. It excludes capital infrastructure, that is building, machinery and office operations from the LCA. The assumptions, they are based on the composition of MSW. Okay, it is 50% organic, 20% plastic, paper and mixed. Net calorific value, it is 8 megajoule per kg. Grid emission factor 0.82. Bottom ash utilization 20%, maybe in constructing the road base 20% of the ash is used. So, here in this case study for this lecture, we are using assumed values, but in a real case study this can be obtained by collecting the samples of MSW and doing some measurements. MSW composition we can obtain by just sorting it out by segregating. Calorific value you can measure using calorimeter. Emission factor can be obtained for a grid using the locally available data based on the region, the country, and ash utilization rate, again it would depend on the existing company and system, like how much ash they are actually using and in which application. So, here these are just the assumed numbers. So, once the goal and scope is decide what is included, what is not, and life cycle inventory, these are the inputs for per unit functional unit, right? 1 megawatt electricity. So, how much waste is required? Almost 1 ton. Diesel for collection. So, this is for 1 ton, okay, 0.8 liters. Transport distance is 25 kilometers. Auxiliary electricity use is there, 50 kilowatt hour for running different equipment in the incineration plant. Limestone is required in the scrubber. So, per megawatt hour, that is per 1000 unit of electricity, you need 3 kg limestone. Activated carbon is required in those back filters and all. Then urea is required for catalytic reduction of maybe flue gases. So, that is 1.5 kg. So, that is the input per 1 megawatt electricity, mainly on this MSW and the auxiliary side. Then on the emissions side, emissions to air per 1 megawatt hour. So, if it is take a flue gas and do the composition analysis, we can obtain this data. Here let us say for CO2 for fossil is 100 kg, like this is the CO2 which is coming from the fossil part of the entire system. Like if there is any biomass in the MSW, maybe that CO2 is not accounted here, but by burning of paper, plastic, cardboard, all those things would be included here. Methane, N2O, so these are like greenhouse gases. Then here NOx, SOx, PM10, SCl, mercury are in the traces in the fly ash. So, those are on the emissions side inventory. On the residues side, we have bottom ash, 200 kg bottom ash is there, almost 30 kg fly ash is there, and when we clean the fly ash using different materials, different like including water, limestone, activated carbon, you get around 15 kg of waste there. So, one approximate assumption or calculation you can do here, like if I ask you what is the ash content of MSW. So, if it is 1 ton of MSW, 200 or 230 kg ash is coming out. So, we can say approximately 20 to 25% of MSW is inorganic in nature or ash. The same thing was shown earlier also, like the composition of MSW, you can see 50% organic, 20% plastic and 20% mixed. So, in each of these portions some inorganics would be there, which would end up in the form of ash. The last thing was on the something on the credit side, because we are generating electricity here. So, the avoided products are the electricity displaced from fossil grid, and for that the emission factor is negative, that is 0.82 kg CO2 per kilowatt hour. So, for 1 megawatt hour it will be just multiplied by 1000. So, 820 kg CO2 we are avoiding. This may be in comparison to a coal fired power plant, So, if the equivalent amount of electricity is coming from the grid which is running on fossil fuel, and that is having the emissions of say 0.8. So, that is the amount of emission which will be avoided by electricity generated from the waste. So, it is having negative value, that is minus 820 kg CO2 for 1 megawatt hour, that is like a credit to us. Now, once the impact like the life cycle inventory is prepared, the next step is calculating the impact. So, in that there are different categories like global warming, acidification potential, eutrophication, human toxicity, particulate matter, fossil fuel depletion, okay. And each of those impact category has a specific unit, and these are the final results for each of those impact categories and some notes like how those numbers came actually. So, let us look at first impact category, that is global warming potential. How did we get this 70 minus 703? So, it appears that since it is a negative value, it means on the global warming potential side the waste to energy plant is actually environmentally beneficial. So, in global warming potential, so the CO2, methane and N2O, and the other last one was the use of diesel in the transportation while collecting the waste. So, those quantities are given to us from life cycle inventory. Now, for CO2 the emission factor or GWP factor is 1. So, for 100 kg CO2 its emission is 100. For methane it is 28. So, 0.2 into 28, how much? 56 and 5.6, that is in kg CO2 equivalent. We are doing for global warming potential, the unit is kg CO2 equivalent. Similarly, N2O, the GWP factor for N2O is 298. So, 0.03 into 298. So, something close to like 309. So, it is 8.94. Finally, diesel use. So, diesel we do not have it in kg, but we have it in liters. So, if we get the emission factor in liters like kg CO2 per liter, it is 2.68. So, if we multiply this emission factor by 0.8, we can get the kg CO2 equivalent or the emissions from diesel in terms of kg CO2 equivalent. So, addition of each of these values in a single unit will give us the final burden or total burden related to the global warming potential. So, GWP is 116.68, but the value which we got was minus 703. So, this shows the global warming potential only for the inputs and outputs coming from the plant, but not for the avoided electricity that we generated from the plant. So, the avoided grid electricity has a positive benefit of 820 kg CO2 equivalent. So, the net GWP potential now would be 116. So, since it is the avoided value, when we put it into the number, it is actually coming out to be 116.68 plus avoided value is minus 820. Okay, that is why this is, it is not like 116 minus 820, but it is like 116 plus avoided grid electricity benefit, which is in negative because of the term avoided, and that comes out to be minus 703 kg CO2 equivalent per megawatt hour. Understood? So, that is how global warming potential is calculated on the net side. Now, this avoided electricity and the avoided CO2 emissions associated with electricity, it will come only in the GWP impact category. The any other impact category which is dealing with CO2 is not there. Okay. So, similarly like here 703.3, that is for global warming potential. For acidification you have 0.6, you can do the similar calculations based on NOx and SO2 data from the life cycle inventory using the characterization factor or emission factor to convert this NOx into this common unit of kg SO2 equivalent and get this number. Similarly, for eutrophication potential, NOx would be converted to phosphate. Then human toxicity, it will depend on the amount of heavy metals in fly ash and the flue gas cleaning residues. Okay. If you remember the LCI life cycle inventory, in this case study we had some heavy metals listed as a part of fly ash. Then particulate matter formation also was given based on PM10 and PM 2.5. Fossil fuel depletion, it is with respect to the consumption of auxiliary energy or fossil fuels in the process, like how much diesel or urea is being used, and for that what portion of fossil fuel has been depleted from the nature's reserve, that gives us the fossil fuel depletion potential. That is how all the life cycle impact can be assessed. For here I have shown it for 6 or 7 categories, but it can be done for all the 18 impact categories, and maybe it happens sometimes that all 18 are not like relevant or important for a particular case study. So, we just consider the relevant impact categories in our assessment. Now, the same activity if we do it for landfill option other than like in comparison to waste to energy, which was based on incineration. So, what is obtained here is net methane emitted to atmosphere is 50 kg per function unit. So, function unit was 1 megawatt hour equivalent for what? For electricity, like for waste to energy plant. But now in landfill we are not generating any energy. So, even if we are not generating any energy and if we are to use the same function unit, so we cannot, since we are not generating energy, we use the equivalent to 1 megawatt hour, that is 1 ton MSW. Okay. So, since in waste to energy plant to generate 1 megawatt hour we need 1 ton MSW. So, we take 1 ton MSW as a basis for calculating landfill emissions. So, again the basis is similar, we did not change. Okay. So, 50 kg methane is emitted per ton of MSW. So, if that is the net methane emission, the global warming potential for methane is 28 in terms of kg CO2. So, if you multiply it 50 by 28, it comes out to be 1400 kg CO2 equivalent per functional unit. So, just global warming potential if we calculate for landfill option, it is 1400 kg CO2, and for waste to energy option it was negative considering the avoided electricity credits. So, based on this comparison we can easily conclude or infer that waste to energy plant, it performs significantly better than landfilling in terms of GWP or global warming or greenhouse gas emissions, and it is mainly due to avoided methane and fossil electricity displacement. So, since the waste which was going to landfill and would have released methane emissions is now going to waste to energy plant, the waste to energy plant case already has a lot of credit on avoiding this methane emission on the GWP side. Okay. And then there are some additional credits when it generates electricity from that waste and it displaces the fossil electricity from the grid. So, there are two avoided emission benefits which comes with the waste to energy plant. However, toxic emissions and ash handling, these are the critical issues which are associated with waste to energy plant and they need some strong pollution and control strategies. So, now this comparison against landfilling can be considered as one of the parts of our last phase, which is interpretation, right. So, if we have to compare waste to energy with landfill on the basis of climate change, land use, energy recovery. So, in all the cases waste to energy seems to be better. In terms of emissions we have already seen minus 700 plus 1400. So, there is a substantial benefit in the category of climate change or global warming potential. For 200 kg ash which is generated in waste to energy plant, this ash can be used. Even if it is not used, it will take substantially less land compared to the large landfill area taken by the same equivalent amount of MSW, which will have that 200 kg ash. Okay. So, on land use also it is better. On energy recovery, there is energy recovery from waste to energy, but there is no recovery of energy on landfill site. So, definitely this is better. So, it comes out that in these two cases waste to energy is better performing alternative in almost all the 3 categories that were of concern to us. So, the key hotspots that were obtained from this LCA when it was done for incineration based waste to energy plant, the key hotspots were NOx emissions, heavy metals in fly ash, diesel from collection trucks. So, can something be done on, like once these key hotspots are identified, it gives decision makers a platform or basis to think of solutions in a specific area. So, for NOx they can have something like selective catalytic reductors or reduction units which can reduce 70% NOx. For collection of waste, instead of using diesel trucks, electric vehicles can be used. The ash utilization, it was 20% only in the road basis. It can be increased to 70%. So, what will happen? It will reduce those impacts further. The key hotspots won't be any longer a hotspot if these improvement measures are taken. Finally, improve the segregation, because if we could remove the inert component of MSW, it will help increase the calorific value of that waste, which can be used as a fuel for incineration. So, that is what if you have heard of something called as RDF, refuse derived fuel. It is obtained from MSW by removing the inerts like stone, glass and the wet portion of the MSW, and you just squeeze water out of it, and only the combustible part of municipal solid waste is collected and compressed in the form of cakes or blocks, and it, when it is dry, it comes out to be a very good fuel for thermochemical processes like combustion, gasification or pyrolysis. So, to summarize, when we considered this case study of, this was the second case study of life cycle assessment that we covered after doing the first case study. It was on coal fired power plant, right, and this was on waste to energy plant, and we compared it against the landfill option. So, one case study was just to find the total environmental impacts by doing LCA for a given system, and second was we do LCA of one given system, we compare it with an alternative which is traditionally existing for municipal solid waste, that is landfill, under the different impact categories. Okay. So, two types of case studies we have taken, and both of them are related to different components of environment. So, can well go along like with the other concepts that you learnt in this course. So, I think we will stop here for today. Thank you.